Marketing firms spent years branding the cloud as a pristine, invisible space to distance users from the massive industrial machinery handling their data. Uploading a photo or streaming a movie sends bits of information directly into a spinning metal hard drive bolted to a server rack inside a climate-controlled warehouse. This network functions as an integrated planetary-scale machine, a dense collection of hardware that occupies more physical space than any other piece of human engineering. Relying on the cloud as a metaphor obscures the reality of our communications. When we ignore the hardware, we overlook the physical vulnerabilities that can disconnect entire continents in a single afternoon. Tracing the path of that data leads away from the atmosphere and down into the mud at the bottom of the ocean. These glowing lines are submarine cables, heavily armored steel and plastic tubes resting in the oceanic trenches. They carry 99% of international internet traffic. Laying these lines requires specialized ships to spool thousands of miles of wire across underwater mountains, while remote-controlled submarines bury the cable in the seabed. While some of our signals bounce off satellites, our global connections primarily rely on continuous, physical tethers dragging across the oceanic crust. Slicing open one of these massive submarine cables reveals that the heavy exterior is just a shield for a microscopic core. Inside are fiber optic cables, perfectly clear threads of pure glass, each thinner than a human hair, providing a dedicated highway for global data. Data pulses through these threads as flashes of laser light, ricocheting off internal walls of the glass at nearly 300,000 kilometers per second. An increase in internet speed represents a mastery of physics, specifically the efficiency with which a photon can navigate a glass tube without losing its clarity. With millions of intersecting wires, each flash faces a logistical hurdle, finding the exact glass tube required to reach one specific phone on the other side of the planet. An IP address serves as a digital GPS coordinate, assigned to every single device connected to the network. Routers sit at every major intersection of these glass cables, functioning as high-speed sorting facilities for the web. As shown in this diagram, a router reads the destination IP coordinate on a piece of data and instantly calculates the fastest physical wire to shoot the light down next. These machines provide the geometric logic required to transform undirected flashes of light into a functional global network. A single 4K video file is large enough to monopolize a glass thread, effectively blocking all other traffic from using that specific wire. This illustrates packet switching. Your computer shreds the file into microscopic pieces. These packets travel independently down different physical routes, bypassing congested cables. They arrive at the destination at slightly different times, reassembling in the correct order to recreate the original file. Packet switching provides the mathematical coordination needed to manage shared infrastructure, allowing millions of users to utilize the same physical wires simultaneously. Zooming out from those individual packets reveals the true scale of the system. This coordination joins billions of people through lasers, deep-sea glass, and constant mathematical shredding. Maintaining this network involves constant physical intervention, repairing lines severed by ship anchors or shifted by tectonic activity. The internet exists as a heavy industrial infrastructure. It is a system built of glass and steel, vulnerable to the same physical forces as any other machine of its size.